1 summation k equals to 0 to n Pij n. This converges to pi I. So so now on I'll take Xn an irreducible Markov chain. So it converges to pi I, and where pi I is equals to 0 for all I in S if the chain is transient or null recurrent. Sorry? Thank you. Should be pi j for all j in S for all I in S. And so this is 0 for transient or null recurrent, and is the unique solution of pi p equals to pi for positive recurrent, and then pi is the stationary distribution. This is a fantastic result. This is in a summary of what we have seen. This is a mixture of whatever we did for the mean ergodic theorem and as well as the other corollaries of it. So this is all very good. However, the question remains that we don't want this kind of average. That wasn't our interest. So we know that for the average, what we really want to think is about Pijn. Does that converge to pi? Is a question. Why is it a question which we want to answer?
Sorry,
yeah.
Once again, the pi j is defined as the diagonal of the pi j is equal to capital.
No, I'm sorry. This should be pi I. Let me pi ij, but then pi ij becomes so pi ij is pi. Right, this should be pi j. Right, yeah, pi j. Because remember, the pi matrix, the big pi matrix, is nothing but pi, pi, and pi. If the rows are repeated, that's how the matrix look like, and that's the structure. So it is true, it is pi ij is what we started with in the mean ergodic theorem, but the subsequent discussion resulted to this fact where we now exactly know, so this is for the irreducible case, that it also classifies us between transient, null recurrent, and positive recurrent. Okay, these are the three possible ones. Okay, so now why do we want to think about this? Now, you see, what is this? This is probability of xn equals to j given x naught equals to I. If it is so that this does converge to pi I, which is the stationary distribution, sorry, pi j, and that happens for every j. If that does happen, then we can say in some sense, at least the least, which is the distribution of xn, they converges to the distribution pi. So for every j, probability xn equals to j given x naught equals to I converges to pi j will tell us that the distribution of xn as n tends to infinity starting at I becomes the stationary distribution eventually. We cannot say that the random variables are doing something, but at least the distribution is doing something. And there are many names for it. We, the probabilists, call this is weak convergence. And then we write this, that xn converges weakly to pi. Okay? Now this is not quite correct to write this because we had not xn, but xn starting with at any point. So I can write x naught equals to delta I for every I in S. This is what we want, that xn converges weakly to pi. Now please, those of you who are staunch analysts, our weak convergence is what you call your weak star convergence. Okay? So your weak star convergence is what the probabilists call weak convergence. no communication between the two groups resulted to this wrong use of terminology, perhaps. We call it weak because this is somewhat the weakest of the possible different type of convergences probabilists try to derive. All right. So,
Is the same as what you call convergence in probability?
no. Convergence in probability is more strong than this. However, it may not hold always. In this case, it is not quite even possible to think about it because of various other whatever measured theory. This is convergence in distribution. So if convergence is same as convergence in distribution or in law, we'll see the one we will derive is far stronger than just weak convergence. Okay, so here is the real theorem. And this has many names. Some say this is the fundamental theorem. Of Markov chain. Some books say the limit theorem for Markov chain, and some, which is becoming more and more obscure, say that this is Erdos Feller Pollard theorem. And these are all names are of many cultural things that, yeah. So anyhow, so what is the theorem? So let Xn be an irreducible Markov chain on state space S, transition matrix P, and all right, it's just state space S and transition matrix P because we really don't need initial distribution theorem. Would be true for every initial distribution, such that I do need some assumption, and the assumption I'm going to make now is slightly less than the real power of the theorem, but I don't want to go into some of the technicalities. So I'll assume PII is always positive for every I in S. Okay, so such a thing is called lazy in the sense that it has a positive probability to stay put in where it is standing now when it wants to move. Okay, so at each state it has a positive probability to stay put. All the chains you will be discussing in the workshop from Arvind's lecture today onwards will have this property. So that will be in the domain of the theorem we are going to discuss now. Then Pijn converges as n tends to infinity to pi I for to pi j for all ij in S, and where pi I equals 0 for all I in S if the chain is now transient or null recurrent, and pi I is strictly positive and pi is unique solution of pi p equals to pi if chain is positive recurrent. So this is a fantastic result, and let us try to quickly prove this. The proof I am going to present is one of the most beautiful proofs in probability theory. There are few beautiful proofs, and many of them, proofs of Erdos are really good, but the proof I am going to give is not Erdos's proof. Unfortunately, the original thinkers did not give the best proof. The proof I am going to give is the proof of another great probabilist and analyst. This is Dub's proof by a concept which then later on became a very important concept in probability theory, and you will see probably some use of it in also the use of the representation theory called coupling. So let's see. Yeah. Yeah.
Because at
Yeah, aperiodic is the term which I am not using. This is being assumed under this assumption. So the reason is aperiodic is very technical to state that what exactly it means. So I'm just skipping that because for the sake of time and as well as the kind of things we will discuss in this workshop, I have this assumption and it is necessarily aperiodic. Yeah. All right. So what are you going to do? We are going to do a very simple thing. So I'm going to run two independent, and when I say independent, I mean stochastically independent chains as two copies. So one I'll call xn, and the other one I'll call yn. So they will be both Markov chain of of xn. That means it's on the state space S with transition matrix P, but I'm going to give different initial distributions. So fix and the proof I'm going to write is only for the positive recurrent case. The other case I'm going to skip for lack of time, but can be done in the similar way, but let's not bother. I'm just going to do the positive recurrent case, which is the case which we will be discussing in the rest of the workshop. So, so fix an I, or maybe I naught in S, and let say x0 is delta I naught. Okay. So I mean x0 is equals to I naught. The distribution of x0 is delta I naught, and y0 follows pi. So since I'm assuming it's a positive recurrent chain, I know from my general discussion before lunch that there is such a pi. Okay. So I start my y chain in the stationary distribution pi. So the yn is a stationary Markov chain, and however I start xn at a specific state I naught. This is a probabilist notation. This means distribution of y naught is equals to pi. So we write this thing as y naught follows pi. Okay, yeah, that good. Thanks. That's an important thing too. Okay. Now I'm going to look at the chain Zn, which is taken these two things as a vector. Now that's also a Markov chain. So that's an easy exercise. A Markov chain with transition matrix. So now I have to do two variables, right? So P, or maybe P would become more confused. So maybe A. So I comma j to say alpha comma beta. So they are running independently, right? So I want them to be run independently. So they are P I alpha and P j beta. So X chain moves from I to alpha by the original transition matrix Pi alpha, and Y chain moves from J to beta by the original transition matrix P, and does it independently. So that becomes product of the probabilities. Okay. So the only thing to observe that probability Z0 is equals to something. So let's do it I0 and I don't know some beta 0. This is exactly equals to, or maybe I'll do I delta, let's just do I0 is exactly equals to pi beta. Right? That's the starting of this chain, because the X always starts only at I0, and beta 0 this should be, and Z0, the Y0 follows pi, so that's the probability. Yeah, you can think it in that way. This is a stochastic independence is tensor product. Yeah. All right. Independent copies. Independent. Now, if you look through at the matrix way, so is it tensor product? But no, it's not tensor product.
tensor product.
It's not that, but it has another name.
It's a block
It has a name. It has a matrix algebra. People have a name for it.
It's block diagram. No, what is S is S cross S.
It's, huh? Yes, yes,
Not S cross S. It's two copies of S.
yes.
S comma.
No, Orvin, the state space, let me write down. The state space for Zn is S cross S. So it is S cross S. It's S cross S. The matrix A, the matrix A.
Looks like tensor.
Yeah, I think so too. A is whatever this A comma this is a S cross S cross S cross S matrix. Okay, so yeah, I think it is the tensor product, or the Kronecker product is what they say, right? Right. Okay, very good. So quick observation that probability xn is equals to j is exactly equals to p I0 j circle n, right, for every j, by definition. And probability yn is equals to j is equals to pi j for every j. Why? Because y is a stationary process. Y is stationary, and so its individual distributions remain same. Process is moving, but now change in the distribution, because y is starting with pi. And so because pi solves the equation pi p equals to pi, I'm rehashing every time, getting only pi. Okay, so now I claim, so it is enough to show, so to show limit of n tends to infinity. Yeah. So the initial point for the z chain, it starts at the first coordinate always at I0. The second coordinate may be something which is selected as according to the distribution pi, because I want my y naught to start according to the distribution pi. So the probability that z naught has two coordinates I naught and beta naught has probability pi beta naught. Yeah? Okay. Now enough to show the following then. Probability xn equals to j minus probability yn equals to j is equals to 0, right? Because that's all I want to show, right? I want to prove that for every fixed, well, here I had I, so every fixed I naught, probability xn equals to j given x naught equals to I naught converges to pi j, right? This is exactly that. That is p I naught j n, and this is pi j. Okay, and now the beautiful trick of Doob, which was later on rehashed many times by many famous probabilists and in many proofs. So let t be the first time xn is equals to yn. So imagine, so forget about all these technicalities of metrics, etc. Just imagine yourself that you have started your x chain at I naught. You have started your y chain by selecting a state according to the stationary distribution pi, and run the two chains independently. Okay, and wait till they meet. Just wait till they meet. And that time I'm writing as t. So a claim, which I'll prove after I proved what I want to prove, that probability t is finite is equals to 1. They are going to meet. This can happen provided there are some assumptions. This assumption is important, which is important to have the positive recurrent keys. They will meet. Okay, now I claim next is very simple. Rest of the things has no calculation at all. I should be done in another 5 minutes, Arvind. I'm sorry for taking more time. Right. So let's look at this. Look at probability xn equals to j, comma t lesser equals to n. Well, this is same as probability xn equals to j, and maybe at some, oh, I should write a big sum. So at some point k, they met, so xk equals to yk is something, and t is equals to k, right? This is right. Agreed? Yeah, so I'm looking at this probability. Probability of xn equals, I want to calculate this probability, right? Probability of xn equals to j. I'm going to do it in two parts. I'm going to look at first xn equals to j and t is less or equals to n. So if t equals to k, then at that time point, xk and yk are same, right? Would you mind if I now then write probability k equals to 0 to n? No, I don't need to write middle thing at all, but the fact that t equals to k by definition gives me this. Okay? All right. Now, let me see, when I'm doing this setup, there is nothing wrong in doing this setup, but let me also do the following, that till the time they meet, I am in this setup, okay? I'm in this setup of running independent, and now let me say that x, we will write xn is equals to y, or we will take xn equals to yn for all n greater or equals to t. Now I claim if I do that, my this calculation of the probabilities don't change. Why? Let us see. So at time t, they meet, okay? And after that, they are going to be together. But marginal probabilities, that means the probabilities of the individual random variables are not going to change by doing that. And why is that? They have the same transition matrix, but here I'm using something which I did not tell you, but means I did tell you, but we didn't tell you that I have already told you that. The Markov property I wrote for you has the following fact that, okay, so let's remember our Markov property, that wherever I'm standing today, my presence, if I know what is my presence, my future is perfectly independent of whatever has happened in the past, right? All I told you is that that is true whenever you have given me a time point fixed, maybe 10, 20, 15, 10 billion, so on. There are some times which are random, even that, then this is true. And those are very interesting time points. And such is this one. And what is the property of this one? So if I ask you a question that can you tell me whether t, m will be too confusing, so let's write m. So if can you tell me whether t equals to m? What information do you need to know t equals to m? You only need to know the values of x from 0 till m. You need to know the values of y from 0 to m, but not nothing in the future. Such a times we call stop time. That means by looking at the data x and y, you can decide whether the time has appeared or not for you to do what you want to do. So this t equals to m only depends on x naught to xm and y naught to ym. So because of this, if I say that I do the following, that after that they met, they just remain together, and in other words, they are coupled, they are now coupled, they move together, then I don't change the marginal probabilities. So if I say that, then would you mind if I now write this is yn equals to j, xk equals to yk is equals to t, comma t equals to k, right? Because after they have met at time t equals to k. After that, y and x are exactly same. And what is this probability? This is same as probability y n is equals to j, comma t less or equals to n, right? I'm just replacing the symbol x by symbol y. It's like almost symbolic in that sense.
I don't understand. Yn and xn are independent, right?
till the time, that's how I started. Then I'm saying that now let's change it, that if after they meet, you just write xn and yn together. They no longer are independent. Of course, they are completely coupled now. They move together.
You're claiming that this probability does not change.
Yes, that's because of, you can just do a simple calculation by the stop time. By the way, I should write this. This is called a stop time. But I don't want to go into the technicalities of it, so that's a little bit of caveat there. Now, this is very good, because if this is true, then probability of xn equals to j minus probability of yn equals to j in absolute value is less or equals to probability xn equals to j, comma, t bigger than n plus probability yn equals to j, comma, t bigger than n, right? Because I'll cancel the t less or equals to n's.
So you're not really said y is equal to xn, you just replaced xn by yn in that equation.
Yeah, whatever way you want to think about it. Yeah, just couple the two chains is what we usually say.
That sounds like physics.
Yes, probabilists are all, a lot of the times are like that. Now, if I sum these things up on all j's, so I'm going to prove something much stronger than what is required. Then what happens if I sum them up on the whole state space? Well, these things would be summed up. So xn can only take values on the state space, so that xn equals to j will be gone. So that becomes probability. So this is less or equals to twice probability t is bigger than n, right? And I'll bring this half over here, and I'll get this beautiful inequality. Now, if my claim is right, that the probability t is finite is 1, then probability t bigger than n would go to 0, right? And this goes to 0 as n tends to infinity.
Sorry, how do you get from the second inequality to?
From here, I just sum over all j. So these guys would be disappear because xn can only take value over s. So I get only probability t bigger than n. Here also I get probability t bigger than n. So I get twice probability t bigger than n, which I bring as a half. Okay. Now a little bit of quick definitions. So the theorem is proved. Okay. The theorem we wanted to prove is proved. Modulo the claim. But before I prove the claim, let me tell you quickly some analysis definition. The particular norm I have written down is a very important norm, and Arvind would be using it. So half summation. So let mu and nu be two probabilities on S, then half mu I minus nu I. This is a L1 distance, right? Half of the L1 distance. This is half of L1. This is also equals to the following. This is supremum over all subsets of S, absolute value of mu A minus nu A. This is a simple result. And then one knows from the general definition says this is so-called the total variation distance between, or maybe I'll write distance total variation mu nu. And this is what I have now proved for you is that the law of xn, xn starting at a fixed I converges in the total variation norm to the law which is the stationary law. And that's much stronger than the weak convergence, because as we know, the analysts, they all know that the weak convergence is the weak star convergence, which is much weaker than that convergence in total variation. Now, this is, by the way, in this case, is not such a big deal because we are working on countable state space. Okay. And now the whole game is to, what Arvind would be doing is to try to find out how fast it moves. So one wants to figure out, so what have we done? We have proved that this happens, but then how fast that happens. So maybe you want to find the following, that fix an epsilon. So that's the amount of error you will allow yourself, such that first time, or maybe I'll write minimum. So this the mixing time, T mix epsilon, is the first time something happens that soup over I in S, the total value, maybe I'll write it here. So this is minimum over n greater or equals to 0, and then soup over I in S, and the total variation distance between distribution of xn given x naught equals to I and pi is smaller than epsilon. That's called the mixing time. And for some unknown reason, David Aldous decided that we will not be interested about any general epsilon. We'll call T mix as T mix of 1/4. 1/4 was good enough for him, and he's one of the kind of at the originator of these ideas, and that stuck with the community even now. All right. But nowadays, of course, people understand that in order to get their asymptotics, one should keep epsilon and to see how does it scale like n as well as with epsilon. Okay, so modulo claim. So let me just quickly do the claim. And the claim again is almost immediate of whatever the theory we have done by the in the morning. Okay, so proof. Huh? Oh, it's just a trick. You see, you just look at the set A for which this is larger than this, and that would do. It's just a trick. I'm not saying one another coupling here because that would digress me a lot. If Arvind uses it, he can prove that it has another beautiful probabilistic interpretation, the total variation norm. But that I'm skipping here. Okay, so proof of the claim. So fix a state S, say, in S. Okay, and let Ts be the first time my Zn is Ss. Okay? If that is the case, I claim T is definitely less or equals to Ts, right? By definition. Because by Ts, Xn and Yn will couple.
So you're proving now
proving the claim. Claim that this is 1. That is very important, right? Otherwise, the limit going to 0 will not be true. So T is less or equals to Ts, right? Because by time Ts, they of course have coupled if they hit Ts. So T is the first time they couple, so they may have coupled at some other state, we don't know. Right? So T is less or equals to Ts. What I'll tell you is that probability Ts is finite is equals to 1. And why is that true? The proof is very simple, because in our original independent chain, my Zn chain is a positive recurrent chain with stationary distribution pi alpha, pi beta for the state alpha beta. If I look at pi alpha, pi beta, then for the transition matrix, which unfortunately I have erased, so let's recall a ij to alpha beta was p I alpha p j beta. For this transition matrix, it's immediate, just multiplied with this, and then sum it up with alpha beta, you will get 1 times 1, which is, sorry, you will get pi ij, because of pi itself is a stationary for p. That's why. All right, so it's a positive recurrent chain. If you're a positive recurrent chain, the heating time has to be finite. not just finite, its mean is finite. The only problem which we have to be very careful here, that, well, this is very good that this, I'm claiming that this is positive recurrent by giving all this thing. We need to make sure that the things are irreducible, right? That was very important in our entire discussion. Now, it will be irreducible provided this happens. If this doesn't happen, this chain may not be necessarily aperiodic. The aperiodicity would result to this joint chain to be irreducible. The following problem can happen if we don't have that. Say, for example, the following chain, very simple chain. 0 goes to, okay, so there are two states, 0 and 1, 0 and 1. 0 goes to 1, 1 goes to 0. So if I start my X chain at 0, and the Y chain is at 1, they will never meet, right? They will constantly cross each other, would never meet. That's a problem. Such problem is removed by making this assumption, and that's why the claim is true, and that's it. So it's as you can see, there is really no calculation. This is a fairly abstract argument, and this is a powerful method coupling, which has become a central theme in probability theory in modern days. Okay, thank you.
Okay, so let's thank